Okay, section 11.1 is functions of several variables. So we're going to go through a lot of the same things that you saw when you first learned about functions of one variable. So you will see functions of several variables. For example, a function of two variables would be written like this. Okay, and just like when you did functions of one variable, f of x was kind of our fancy way of saying y. F of xy is kind of our fancy way of saying z. Okay, the domain, let me erase that part. Your domain would be ordered pairs instead of specific values of x or specific values of y. It would be different combinations of x and y, and it's important that we consider them together. And you'll see why when we get to some of the examples where we give the domain. You can't just say what x can be and what y can be. You need to say what x and y can be together. Okay. Your range is your output still. Range is the values the function can take on. Okay. Your x and y are going to be your independent variables. So you have two inputs, and z is your dependent variable. Okay, some notation that you'll see that you might not have seen before. So a little notation alert here, kind of. You will often see the domain written as I don't even want to do that really, but I think the book introduces it as this and then it kind of changes it. Let me just double check here while I have my book open. Yeah, they do. Okay, so your function f xy exists. That's a little sign that you should know, okay, or are in the domain. Okay, so it's like your set notation. Okay, so this is the values of the function, which would be the fxy. You don't have to worry too much about this, so you'll see how it's used in some examples. Okay, and this is your ordered pairs. Why did I spell pairs wrong? Okay, this kind of is read are in, are exist in. This is the domain. Okay. Let's see here. Look at some examples here of just like writing the domain and range of these. So an example, we've seen this one before. Okay, think for a second about what that's the equation for. Okay, and that's the equation for the volume of a cylinder. Okay, so if we were asked to find the domain and the range of this, now this has a context, right? So your domain would be all ordered pairs RH such that R is greater than or equal to 0 and H are greater than or equal to 0. Okay, because in order for the cylinder to exist, right, we've got this context here with this one. Your range would be V such that V is greater than or equal to 0. Okay, another example, one without a context to it. Okay, for this one, your domain, think about it here for a second, xy, such that x and y together have to be greater than -1 or equal to. Okay, and that's what I mean by looking at them together. It's not enough that x is greater than -1 and y is greater than -1. It's the ordered pairs such that when you add them together, they're greater than -1. Okay, but also x cannot equal 1 because of that denominator. So we can kind of list those restrictions there. Okay. Let's see. Your range on that one then, let's see, in the numerator you're always going to get a positive number, but it would be possible to get a negative number in the denominator. So all z such that, we can just say z exists in the domain of real numbers. Okay. There you go. So like kind of what I was getting at before, if you were to write this wrong and you did something like the domain is x, y, such that x is greater than -1, y is greater than -1, and x cannot equal 1. Okay, first of all, I'm going to put a big red X through that so that you don't think that that's right. Okay, but think about it. X could be -1000, and that would be fine, just as long as y would be, let's see, 999 or larger, right? Okay, because then the -1000 plus the 999 plus the 1 equals 0, and you're good. Okay, so that's why what I mean by consider them together. Okay, then too, one thing that the next thing you would do then is evaluate this function at different values. So this is an example in your book. They do f of 3, 2. So you'd have the square root of 3 plus 2 plus 1 over 3 minus 1, which should get you the square root of 6 over 2. Okay, so that's how you're going to do your domain and your range. I'll do one more example for you really quick that's in the book, and we'll just talk about the domain. Definitely read your book to see some more examples here. But we have g of xy equals the square root of 9 minus x squared minus y squared. Okay, so since we know that 9 minus x squared minus y squared has to be greater than or equal to 0, we can do something like that. Okay, so your domain would be all ordered pairs x, y, such that x squared plus y squared is less than or equal to 9. Okay, and you'll notice too that you can graph these domains. You can graph these regions. So we know x squared plus y squared is a circle with a radius of 3 centered at 0, 0. So if I were to ask you to graph the domain, 3, 3, -3, -3, it's that circle, okay, with a solid boundary, right, because of less than or equal to. If I were to graph this one, x plus y is less than 1, that graph would be a line. Okay, so you can quickly find our intercepts of that line. If x is 0, y would be -1. If y were 0, x would be -1. We would solid line through that one. And x plus y is greater than -1. So we would shade that half plane there. Okay? So you can graph that two-dimensional region that would give you the domain. And I mean, you can start to think about how that's going to get us some three-dimensional graphs here eventually. Okay? Put in any xy pair that's in that green circle, and you can get how high the z value should be, right? So like if I plugged in 0, 0, then z would be 3. Okay, if I were to plug in 1, 1, then z would be the square root of 7. Okay, and you start to kind of think about the depth of that, how high up the z-axis we would go then, and we're getting into our three-dimensional graphs there. Okay, which now we're going to get to next. So you would, when you graph, okay, all z values must be above or below the domain. Okay, so again, we were looking at it as a flat 2D graph. We can think about how high above the domain your z-value would be or how far below the domain it would be in the negative direction. Okay, and you have actually graphed these before. When you did three-dimensional graphing, I know you started in Algebra 2. You know, an example would be f of xy equals 6. And I mean, you did them in the previous chapter too. I shouldn't forget that too. It's been a while since I made those videos, but you did that graphing too. Okay. You've done graphs like this. So you can think about, well, your domain here is actually all real numbers. Okay. You can plug in anything you want for x and y. If you remember, when we did this in Algebra 2, this is a plane. And if you remember how we did a plane in Algebra 2, you found the intercepts, and you kind of made a triangle and you shaded it. Okay, so if x were 0 and y were 0, z would be, oh, I got a little sloppy there, would be 6. Okay, so we could plot 0, 0, 6. Okay, don't forget your axes here, x, y, and z. All right, if we had x is 0 and z is 0, then we would just have 0 equals 6 minus 2y, right? So y would have to be 3. Okay, so we can do 0, 3, 0. And then we can get another one on here. If we have y is 0 and z is 0, then we'd have 0 equals 6 minus 3x. So x would be 2. Okay, so we can get that one. Okay, so when there's nothing being squared in there, you know it's going to be a plane. And then, like I said, if you remember, kind of draw in that triangle and shade it, but also know that this plane goes on forever. This is just kind of the slice of it that's in the first quadrant. Okay, we can do some more examples when you get to the classwork. Actually, you know what? We can go ahead and graph that guy up there, your g of x up there. Right, so and we talked about some of the points already, right? We plugged in, if you plug in 0, 0, 3, 1, 1 square root of 7. Any combinations of the ones would work, right? If x were 3, the other would have to be 0, right? Y, if x were 3, y would have to be 0. Because otherwise you can't take the square root, and then if x is 3 and y is 0, we get 0 for z. And that is also if x is 0, y is 0. So if you plug in 0, 3, you get 0. Okay, and again, plus and minus is there. Okay, if we were to graph this, this is actually a hemisphere. Okay. And it's only the top, because be careful, some kids get tempted to say, well, make that z equals the square root of 9 minus x squared minus y squared. Square both sides. So we have z squared equals 9 minus x squared minus y squared. So x squared plus y squared plus z squared equals 9, and that's a sphere. Again, let me cross this out. You can't do that because Z will always be positive. Okay, so don't change your original function. Your square root function gives you positive outputs, non-negative outputs. Okay, so when you square both sides, you kind of create that extraneous solutions that don't work. Okay, so I drew my best to draw. It's always hard to draw circles in that 3D space. Someday I'll get good at it, but today's not the day. Okay, so actually I'm going to use green like I did up there. So that same green circle that I drew before, trying to make it flat. Oops, why did I do that? Okay, so that would be 3, 0, 0. This would be negative 3, 0, 0. This would be 0, 3, 0. This would be 0, negative 3, 0. Okay, so that corresponds to the green circle that I drew right here. I'm just looking at it in a 3D space. Okay, and then I know that I'd have the points 0, 0, 3. Okay, and obviously these we already drew. Okay, and these are going to be too difficult to draw, but we know it's going to be a hemisphere, right? So we can kind of, oh, these are so hard to draw sometimes. I'm going to make it like this so it's super obvious. Okay, or maybe it's not super obvious, but it kind of is a dome shape to it. It's a hemisphere, just like I said. Okay, now another way that you can graph these so that it's not such a mess trying to graph in 3D is you graph what's called a level curve or level curves, which are like a contour map. Tour map. Okay, so you have your f of xy. Okay, so you just set that equal to some constant. And then think about at that height, because remember that's z. Okay, so at that height, what does your curve look like? Okay, so if we were to do that same graph that we just did using level curves, what we would do, and a lot of times you're given the values. So we'll do this one for k equals 0 is a good one for sure. 1, 2, 3. Okay, so we'll draw 3 level curves. So starting with if k is 0, then we have, oh, and again, we're going to use f of xy equals the square root of 9 minus x squared minus y squared. So if k equals 0, then we have 0 equals the square root of 9 minus x squared minus y squared. So 0 would be 9 minus x squared minus y squared. So x squared plus y squared equals 9. Okay, and we know that that's a circle centered at 0, 0 with a radius of 3. So that would be the level curve. Do a nice big graph here. When k equals 3. I'm sorry, k equals 0. Okay. My scale's off by a little bit, but it should look somewhat circular. Oops. Okay, and usually you label it. So that'd be your level curve when k equals 0. Okay, now we do another one, because the next one is when k equals 1. So 1 equals the square root of 9 minus x squared minus y squared, which would mean 1 equals 9 minus x squared minus y squared. So we'd have x squared plus y squared equals 8. Okay, so we know that that's a circle with a radius of the square root of 8. So that is actually going to be, the square root of 8 is pretty close to the square root of 9. Okay, actually, I'm going to use my calculator quick. The square root of 8 is 2.83. Okay, So 2.83. We're going to follow this curve pretty closely. Okay, and then that would be your k equals 1. Okay, next one, k equals 2. So 2 is the square root of 9 minus x squared minus y squared. So 4 would be 9 minus x squared minus y squared. So x squared plus y squared equals 5. So circle again, centered at 0, 0, 3 is a 5. I'm sorry, square root of 5, which is about 2.23. Okay, so there's your level curve at k equals 2. And then finally, your level curve at k equals 3. So we would have 3 equals the square root of 9 minus x squared minus y squared. 9 equals 9 minus x squared plus, minus. So we'd have x squared plus y squared equals 0, which is a point. So your level curve when k equals 3 is just the point. All right, so that's like your contour map. Okay, so I can tell a couple of things from here. Since they're labeled, I can tell like kind of the elevation of each of those curves, how high or low they are, just like you would a contour map. And I can also tell how steep it is, right? So I can see there's kind of a steep change from k equals 0 to k equals 1 as compared to k equals 2 to k equals 3. Okay. So that should be enough to get you going here with drawing the level curves. They're kind of fun. I like them. Okay. We're going to talk about one last thing. A lot of these sections end with talking about, well, what happens if there's more than 2 independent, 1 dependent variable. Okay. So we can have 3 or more variables. We just can't graph it very well. Okay. Actually, 3 we kind of can, but more than that you can't. So an example might be your volume function, length times width times height, right? Okay. Excuse me. Another example would be this function. Okay, so that's the equation for a sphere, right? You can graph some level surfaces for these, especially this guy, because you know what that looks like, right? You could say, you could do f of x, y, z equals some constant, okay? And then that would give you the radius of a sphere. So this one actually has level surfaces, okay, instead of level curves, and they would be concentric spheres. Okay, we're not going to get too much into that, but if you want to look, I believe your book does have a drawing of that. Yeah, that's on page 622. Figure 18 is kind of interesting. Okay. You can have more variables than that, and it does come up. We can have z is some function, and we run out of letters if we try to do x, y, z, and so on. So we just say it's a function of x1, x2, x3, all the way to however many inputs you might have. Okay, remember these are just your inputs. So anytime that you need more than one variable to evaluate your function, we're doing multivariable math there. We would call, it's not, so we have our ordered pairs, our ordered triples. Any ordered with a higher number than that, okay, we would call this an n tuple. okay? And it exists, real numbers, right? So our 2-dimension space, we represent like that. 3-dimension space we represent as this. This is n-dimension space. An example the book gives is just like the cost of something. Like if you're doing inventory or, if you store, let's say bread costs $1.29 and milk costs $3.19 and peanut butter is $2.29, and you're buying 10 loaves of bread, 6 gallons of milk, 3 things of peanut butter, right? We multiply those together and add them up. So the cost of your grocery store trip would be $1.29 times however much bread you buy, plus $3.19 times however much milk you buy, plus $2.29 times the peanut butter, and so on. Well, cost is a function of bread, milk, peanut butter, and so on, right? There's so many things in the grocery store. There's not just those 3. Oh, excuse me, you guys. I'm getting a scratchy throat. Hold on. Okay. So with so many things in the grocery store, we can say it's a function of x1, x2, x3, x4, x5, and so on until we get to xn. And we would have these constants, these costs, which would be C1, C2, C3, okay? So you would have to do C1 times x1, right? Or this is like your x1. This is like your x2. This is like your x3. And your Cn xn. Okay. And what you see here is actually brings you back to our vectors here. If we can just have a cost vector, and a supplies, or whatever we want to call it, the product vector, which has all your variables in it. Then we can do a function of that vector is your dot product, right? And you see that a lot in like computer programming. You think about it, what's an operation where you can take 2 lists, multiply entries that kind of line up together, and then sum them, and that's going to be a dot product. So it's used frequently. All right, so there you go for your 11-1, and we'll see you next time.